Welcome to the third part of the high school chemistry class, our course. So we will be learning about Lewis dot structures and molecular geometry in this. So to start a molecular geometry question, the first step is to find the total number of valence electrons. This is what VE stands for. So in carbon dioxide, for this, to find the valence electrons, we look at a periodic table. For carbon dioxide, you have C, which has 4, and oxygen, which has 6 each. So we go back and you would add the 4 for carbon, which is right here, plus 6 for oxygen, plus 6 for the second oxygen. So now you have 16 total. And to start a Lewis dot structure, you need to find what the central atom is. And in this, since C, there's one C, 2 oxygens. You would have C as a central atom. Now each element needs to achieve an octet, which is 8 valence electrons. To draw lone pairs, which is just 2 dots on top of each one, until they have 8. So this has 8 because you have 6 dots plus this line is 2, so you have 8 there. 2 already from the line. There's 2 lines, so you have 4, and you just draw 4 of these. Then this oxygen will be the same as the previous one, but this is not done. This shows what an octet would look like, but in here we have 4 for the carbon. This has 8 for carbon, so you got to somehow reduce this, and you have 6 for each oxygen. So to start, you would cancel out these for both of them, and you would draw another line because this is 2 representing both 2s. And then same thing for this oxygen, you would take that one out, and you can take any of these out, but you can only take one out. Well, one pair out. So this is what your Lewis dot would look like. Double bonded, this is what it's called. Through 2 lines is a double bond. Single bond is 1 line. And a triple bond is 3 lines. So this is your Lewis dot structure, and you can check this if it is correct by counting the total number of valence electrons. So oxygen, you have 2, 4, and then this is being split. So you would have, instead of this being 4 total, you would have 2 over here. So you have 6. You'd have 2 over here from that. This would bond it. 2, 4 for this. So that's 6. You have 2, 2, 2. You have 6 total. So that's how you know it's correct. So this would mean that the final Lewis dot structure for CO2 is the central atom, carbon, with double bonds on each side with oxygen. And you can really put these dots anywhere, the lone pairs, but you can only have 4. Well, 2 lone pairs, 4 total valence electrons on the outside. So with this, you can determine the molecular geometry. So this molecular geometry, you have, you look at the central, you look at the central atom, you have 0 lone pairs. So 0 lone pairs, which is, I'm just going to abbreviate it as LP, lone pairs. And you have 2 things bonded. So you have an oxygen bonded and another oxygen. So 2 bonds. So now you usually look at a chart that is similar to this. And so let me just erase all this. So you had 2 bonds. So it's right here, number 2. Let me use a different color so it's easier to see. 2 bonds and 0 lone pairs. So you would have a linear. So this would mean that carbon dioxide is a linear molecule. And that is all that you have to do for this one. And to go more in detail about the molecular geometry, let's take another look at a water molecule. So in here, you can see that this has 2 lone pairs. 1, 2, 2 LP. I'm just going to abbreviate it that way. That's not the correct abbreviation, but just a shorter way. So 2 lone pairs. And you have 1, 2, 2 things bonded. But that's not true because you also have 2 lone pairs. So you have to add that in. So now you have a total of 4 bonds. But you still have to account for the 2 lone pairs. So you would go back to your diagram from earlier and you would look at the 4 total bonds, which is what we found. So 4 right here. And you have 2 lone pairs. So you go 2 and it intersects at bent or angular. It's usually called bent. So that means that the water molecule is a bent shape. So that is how you would do a Lewis dot structure, along with how to find the molecular geometry of a molecule. And that is it for this video. Thank you.